All right, good evening. So tonight is probably a little bit difficult to convince you that we have a heat problem, but we do have a heat problem, as you know, since Darwin made that trip on the Beagle. The world has been heating up quite a bit. Those are observed data, those are facts, and we know very well about it. And also what's been very well documented is the retreat of glaciers, especially in tropical regions. And the work I'm going to talk about tonight is first is a collaboration with Rudolf von May, who's a postdoc at the Museum of Vertebrate Zoology in Berkeley, at the University of California in Berkeley. And we're interested in using import phylogeny to understand how frogs that live in the Andes that are exposed to this very quick change in climate, how those frogs are going to respond to climate warming. And so this is work that's done in the Andes in Peru. Peru is the country with the largest amount of ice in the tropics. It's a tropical country with many glaciers, with many peaks above 6,000 meters. And so it's actually the country in the world that has the largest amount of tropical ice masses. Now I am going to go back to that Beagle trip because this is Darwin Week. It's kind of a lame quote, but just to tell you that Darwin didn't really get a chance to see that, didn't really get a chance to see those glaciers. He made a very short stop in Lima, and he was not impressed with the country, mostly because of the political bickering of people there, and also because custom officers were demanding a lot of documents. So here's the quote, that they were annoyed by the ocean, but also by problems, difficulties arising out of the disturbed state of that country, the anarchical internal dissensions, which are the bane of all South America, but especially of Peru. So it wasn't easy to work there because of, and so he basically left and went to the Galapagos, where he made a lot of more interesting observations. Anyway, so this work was done in Peru again, despite the political turmoil, which actually subsisted until fairly recently. Peru actually has a relatively good record of how quickly those glaciers in the Andes have been retreating. Those are aerial pictures that were taken as early as the 30s for one of the largest ice caps in southern Peru. And here, well, you can see it's a very well-documented retreat where basically you have the mountain pass, which is the red arrow, that was probably under several meters of ice 100 years ago. And now you can basically walk barefoot through that mountain pass because the ice is gone. So very well documented throughout. And of course now with remote imaging, even easier to document a lot of those retreats. Also, what we have had with amphibians is a very disturbing pattern of extinctions that now already are basically above maybe 200 species already disappeared over the past 30 years. There are several reasons for those extinctions. Many of those are due to disease, to a fungus that's killing many of them. But some people also think that environmental change, including climate change, is part of the problem, is what's causing some of those declines. And here for one of the sites where I've been working for the past decade, showing this is basically a species accumulation curve, which shows how many species you find as you increase your sample size. So here on the x-axis is the number of individuals, and here is how many different species you find. And so as you increase the sample size of individuals, you find more species. So 10 years ago, in this place, in the Andes of Peru, you could find up to nearly 40 species. After finding 600 individuals, what you find now is basically half the number of species. So we have lost half the species richness in this place, which a loss of such extent in just 10 years is quite dramatic. So kind of the overall question here is, the idea is, especially if you have things living on mountains, and they live at different elevations, and they're used to live at those temperatures that you find at high elevations, Well, what's going to happen if the climate is changing is that those organisms are going to try to shift upwards to find again the conditions they're used to. And eventually they might have nowhere else to go, because if they already live at the very top of the mountains, basically they have nowhere else to go because there is no more habitat other than the heavens, meaning they're going extinct. So that's kind of the general question we wanted to ask, and we also wanted to see whether phylogeny was helpful in answering this question, specifically for these mountaintop frogs that live in the tropical Andes. And so, well, that's one of the options they have. These frogs, again, is the ability to move to different areas or to move upwards to higher elevations. So that's one possible response that these organisms have to respond to climate warming. Another one is the ability to evade high temperatures, behavioral, for example, to seek shade or to get wet, and then they lose more heat when they're wet, and so on. Another option is to adapt through natural selection to the new conditions. Now, that's something that is certainly going to happen for things such as flies or other vertebrates with short generation times. Not very likely to occur for things such as frogs that have much longer generation times. So it takes several years for these things to reproduce. Another thing that they could do is maybe they have the ability to tolerate higher temperatures. And that's basically the topic for this presentation, is whether those mountain frogs, those Andean frogs, can actually take the heat, and how much heat they can take. And also whether we can use, again, the evolutionary history of those organisms to address that question. So the general hypothesis is that that ability to tolerate heat is related to the habitat where they live, and especially to the elevation. So as you go up in elevation worldwide, you have decrease usually between 0.5 to 0.6 degrees Celsius every 100 meters that you lose as you go up. And so the general idea here is that you're going to find a general trend where organisms that live at higher elevations will not have such a great capacity to tolerate high temperatures. If you think about what evolutionary history can change in this general trend, is that you might expect the species that are more closely related, they will be more similar in their ability to tolerate high temperatures because they have a shared evolutionary history. So that's one possible hypothesis, which is H0. And the alternative hypothesis is that phylogeny does not matter as much, and what matters most is for example, the environment where those different species live. And so that might possibly reflect more the current distribution of those organisms. And the group that we chose to work with here is this group of frogs that are very species rich in the Andes. It's a very diverse group. It's one of those adaptive radiations, one of the most successful among vertebrates. It's a family Strabomantids. Those are terrestrial-breeding frogs, meaning they just lay eggs on a moist environment. There are no tadpoles. They directly hatch into small froglets. So a very diverse group with also different kinds of behaviors, such as parental care with females, males, and in some cases both sexes attending those developing eggs. It's also a species with a very high beta diversity, very rich in endemic species, especially the mountaintop species. Here we have 3 different mountain passes in southern Peru. Here the distances are basically 40 miles, okay, between those points. And you see they're fairly similar organisms, but they're different species. And so just moving 40 miles from one mountain pass to the next, you have completely different sets of closely related species of this genus Bryophryne. So when we think about history, we basically, well, we need to construct those phylogenies, and we need to be able to date those phylogenies. And I'm not going to go into too much of detail, but Carrie basically already introduced some of those concepts. And here I just pointed, here is basically different genera in this family, Strabomantids. And here I just pointed out some of those genera that live at high elevations, or that have most of their species actually living at high elevations. And as you can see, most of that diversification actually is fairly old. In that case, it's actually fairly similar to what Carrie told you about those marsupials in Australia. So a lot of that occurred at a time when a lot of that diversification in those genera occurred at a time when the Andes weren't even there. Okay, so genera that now, for the most part, occupy very high elevations in the Andes, diversified, originated, their ancestors originated when the Andes were not even there. It's a very short history of the Amazon basin. And so this first figure here, A, is basically when most of that early diversification of those genera occurred. As you can see, there is no Andes here, or they're very low, the Andes. Most of the Amazon basin actually drains out into the Caribbean, not into the Atlantic. We don't have the Amazon River. Most of here is used to be ocean, and basically starting 65 million years ago, that inland sea started to retreat into the Caribbean. And the Andes don't really start to become an important feature until the Miocene, about 20 million years ago, when most of the Amazon basin was basically a giant wetland. And we don't have the current river system until basically 10 million years ago. So now it's basically the most dynamic riverine system on Earth, the Amazon basin. And the first sediments here at the mouth of the Amazon date from 11 to 12 million years ago. So very recent configuration of the actual Amazon basin. But again, the important point here is the time when most of those genera that now occupy the high Andes originated is a time when the Andes were very small hills. Okay, so presumably those organisms actually lived at fairly high temperatures. So here is the place where we did most of the work, which is just a valley that basically drains into the Amazon basin in the eastern slopes of the Andes in southern Peru, and we collected all the species of Strabomantid frogs that we could capture. It's about 15 species. Here is just some advertising for one of the biological stations where we did most of the work. And it has some very nice feature is that it has this lookout over the Amazon basin. You're basically up at 4,000 meters elevation, and you can go look at the sunrise over a green ocean over the Amazon basin. So pretty nice thing. All right, so how do we actually measure the ability of those frogs to tolerate high temperatures? First, this is a fairly easy technique. So we are actually looking at what is that maximum temperature they can tolerate, which we're going to call critical thermal maximum, Ctmax. And if you think that organisms are able to operate over a range of temperatures, which are here on the x-axis, they usually have an optimal temperature at which whatever physiological metabolic function is optimal. We have a minimum temperature under which the animal is no longer able to function. What we're most interested here is on this Tmax, because again, the world is heating up. So we're interested in knowing what is this maximum temperature. And this is fairly easy to measure even in a place without power. You just heat up some water. You put those frogs in a plastic cup. The way that we measured exactly basically the temperature at which the frog stopped functioning was to put the frog belly up and wait for 5 seconds. And if after 5 seconds the frog cannot riding, then you measure the temperature. And it's a non-invasive, they get hot, but they don't die of it, and they entirely recover, and then they were released basically unharmed. We also were interesting, one thing is to know what's the maximum temperature they can actually take, but another important thing we thought was also knowing how close they are to reaching that critical temperature in the habitat where they live. And so to do that, we calculated this metric that we called warming tolerance, which is basically just the difference between the measured Tmax and the temperature they actually experience in their environment. And to measure that, we used agar models. And inside the agar model, I don't know if you can see, but there are these temperature sensors. You can see one here, which are these little things. And so we basically embedded those temperature sensors inside those agar models. And the reason why we use those agar models is because frogs are moist. And because they're moist, they lose a lot of water. And as you know, when you're wet, you feel cold. Well, you lose heat faster than if you're dry. So you can't just use a thermal logger without having the wet part. So that's why we use this agar model. And for the evolutionary part, here the phylogeny was constructed just using one of the most common genes, a mitochondrial gene that's used to construct a lot of phylogenies, which is the 16S. And we used also maximum likelihood tree estimates to construct a gene tree, a gene phylogeny for those 15 species. So again, back to our hypothesis, and now I'm going to basically give you the results. And so again, the possibilities are that those frogs, their ability to to tolerate heat are related either to phylogeny or just to their elevational distribution, or also to their habitat preferences. And so the results are going to be those CTmax data, so those critical thermal maxima data, and also the phylogeny for those 15 species. So here we have the phylogeny, see here on the left we have the phylogeny for those 15 species, and on the right we have the elevational distribution of those species. And so we basically have 4 main groups. These are the 2 first groups where we have these species that are restricted to mountaintops, okay? So very high elevation. These other 2 species are also mostly cloud forest species. This group in blue is mountaintop species, and then in green we have species that occur both at mid to high elevations. And when we look at those critical thermal maxima for over 600 frogs of the same 15 species across an elevational gradient that goes from 1,400 to over 3,500 meters, we see that, and it makes sense, the ability to tolerate high temperature decreases as you go up in elevation. So species that are found towards the lowest elevation examined, so for example 1,500 meters, can take up to between 30 and 32 degrees Celsius. Species that you find at 3,000 meters can only take between 26 to 30 degrees Celsius. But so you do have a downward trend, which is what you would expect. But something interesting is that trend actually it's somewhat interrupted around 3,000 meters, where you kind of have this flat line. And you also have the fact that for grassland species, which are the species that are found above the tree line, there doesn't really seem to be a trend. We also use a statistical technique, which is called independent contrast, which basically allows you to take into account phylogeny when you try to look for a relationship. In this case, we're looking at the relationship between critical thermal maxima and elevation. And what we found is that, well, again, there is a significant effect of elevation, which is a proxy for temperature, on critical thermal maxima, but there actually was no effect of phylogeny, which means it's not because 2 species are more closely related that you're going to find a similar tolerance to heat. So what matters most here is elevation. So it's the thermal environment where these species live. For warming tolerance, the interesting thing is that that warming tolerance actually increased with elevation. So that means that species at higher elevations, despite the fact that they cannot tolerate very great heat, because they live in places that are a lot colder, then the difference between the current temperature they experience and the maximum temperature they can possibly take is actually much greater than species at lower elevations. And for that as well, we have a significant relationship with elevation, and we also have no effect of phylogeny. Okay, so that basically those results suggest that what's most important is either habitat or the current thermal environment of those species. And if we go back to those to that phylogeny that we recovered from that gene tree for those 15 species, and we look at those groups, and in blue we have critical thermal maxima that are below average. In black we have temperature that are within the average, and in red temperature that are above average. And what we can see is, and I also coded with a triangle species that are mountaintop species, and with the sun species that live in open habitats in those grasslands above the timberline. And everything else that doesn't have a color, that doesn't have a code, a little logo, is because they live in the cloud forest. Okay, and so what you can see from this phylogeny is basically that in all those different groups, we find species that can tolerate pretty high temperatures, and we have species that cannot tolerate pretty high temperature, and so basically we have that ability to either tolerate high temperature or not, that is widespread among different groups. Okay. And so basically meaning that it has evolved independently in different branches of that phylogeny, assuming that the ancestral state is to be able to withstand high temperatures, because again they originated at a time when the Andes were not there. And also what you can see is that if you look at the mountaintop species, the ones that really have ability to tolerate very high temperatures are the two species that live in those grassland habitats, okay? Which makes sense, because in those grasslands you have a very wide variation in temperature. They're very exposed habitat at a in a very rarefied atmosphere. So cloudy, it's going to be cold. Sun is going to get warm very quickly. And so that explains also why for grassland species we don't have a very clear relationship between the ability to tolerate heat and elevation. We just have a fairly constant ability to tolerate heat at any elevation at which you find those grassland habitats. And this is just some pictures showing you the difference, the contrast between those open habitat, which basically is bunch grasses, and the cloud forest, and also how that affects the abundance of species that live in the forest and live in the grasslands. So really, the habitat seems to explain a lot of the variation and the ability of those organisms to tolerate heat. Also, because the organisms that have the greatest variation are organisms that live in those grasslands, that also suggests that, and those grasslands are mountaintop habitat, that also suggests that really the species that live at the very top, maybe they're not going to fare too poorly, because despite the fact that their habitat is shrinking, thermally speaking, they're also the species that can probably tolerate the wider range of temperature, okay, because they're already used to those wide fluctuation in temperatures. So they probably have a wider performance breadth, which means they probably can function relatively well over a wide range of temperatures, whereas species in the cloud forest are probably more specialized to narrow ranges of temperature. So we have a stronger effect of elevation on that ability to tolerate heat, stronger effects than phylogeny. Okay, so elevation matters and habitat matters more than phylogeny. So we're the effective canopy cover, which has to do with the habitat being cloud forest or grassland. Also, again, what probably matters a lot is the fact that most of those genera originated at a time when the Andes were not there, at a time when the Amazon had pretty elevated temperatures. So we can assume that the ancestral state for all those groups, even the ones that now live in cold places, was well to be able to tolerate temperatures above 30 degrees Celsius. Again, just a reminder that this is a pretty pressing conservation issue. Among vertebrates, amphibians are the group with the highest percentage of threatened species, and in several cases, we're talking about species that are already gone extinct. Some of the species already gone extinct are species that were extremely impressive for things they used to do, and what certainly was pretty amazing was these gastric brooding frogs from Australia, where the female will basically ingest the eggs, and all the development of the eggs will occur in her stomach. And so those two species of that group are gone extinct. A group that is almost entirely extinct in the end is harlequin toads, which were very charismatic frogs that also 75% of the genus is now extinct. Just very shortly, something that we're trying to extend now. Well, for the phylogeny, we're actually trying to include more genes. Also, when we think about that performance breadth, this talk was just about this critical thermal maximum, but we're basically trying to reconstruct the entire curve using heartbeats. It's a much easier way of measuring metabolism. It's mostly aerobic metabolism. And so here are some data for some low elevation and high elevation frogs. Another thing that we're also trying to measure more accurately is body temperatures, and the assumption that we had that most people still have is that the body temperature of a frog is pretty much the same as the body temperature of the environment where they live. And this is using an infrared camera, and as you can see, that is not a good assumption necessarily, because here you can actually very clearly see the frog in these two cases being warmer than the environment where it was found. So those data probably will improve our ability to understand how close these frogs are likely to be to get to those critical thermal maxima. Here's just an acknowledgement slides, and I would like to, again to mention my main collaborator here, which is Rudolf and May. And well, thank you. I'll be around for questions at the end.